Okay, first, I'd like to say thank you very much to the organizers for inviting me. I'm greatly enjoying the meeting. I'm very impressed hearing about all the good work from 25 years ago or so, and I'll talk a little bit about that. And who can tell me what this picture is of?
Janus.
Janus. So the Roman god Janus, at the start of the year, looks to the past. Two-faced god looks to the past and to the future, and that's why we call the first month January. So that's what I'll do. So we'll start with the past, and I thought I'd spend a minute on my unfortunate academic history. In what sense was it unfortunate? I misspent my youth in physics. And I worked with Walter Cohn, as I mentioned, as a graduate student. But we didn't work on density functional theory. We worked on surface science. And then I went to work with David Langworth. But we didn't work on density functional theory. We worked on surface science. And then I went to Indiana and worked on surface science. But I'd always wanted to do density functional theory, and John Purdue advertised for a postdoc. And I applied. And at that point, I was a little bit past my sell-by date. You're not really supposed to do 3 postdocs. And so I applied, and the way I put it was, okay, I hadn't actually done any density functional theory, but I knew all the right people. Right? And happily, John hired me. And it turned out to be a very productive time. So just looking at the history that we've been hearing about, so this was 1993. So I was not part of any of the sort of really important work that ultimately led to the Nobel Prize. I was just, for once in my life, I was in the right place at the right time, right? And John and I, we said, oh, you know, people in chemistry are beginning to pay attention to this stuff. So we'll send a paper to this obscure journal, the Journal of Chemical Physics, right? We'll just see if what happens. And actually, as I recall, it was rejected, right? And we really didn't quite know what to do, but we sort of argued, and then it got accepted. And then they started accepting more and more of them. But I was just so lucky. Thank you very much, John. I wouldn't have had a career without John. And every lunchtime, we would discuss stuff, and it would have taken him about 5 attempts to explain something to me. But once I got it, I kind of got it. And one thing, if you look at John's papers up to that point, you might notice that they don't actually contain any figures. Or if they do, they might be hand-drawn, right? And the reason for that was he didn't actually have any way of making a figure, right? So all I had to do was write papers and make figures. I knew how to make figures, and we could publish stuff. And the stuff was taking off, and he knew so many things, right, about DFT. And so in the 3 years I worked out afterwards, we wrote 33 papers together. And it was a wonderful time. But then, so having failed for many years to get a job in a physics department, I finally saw the light. A friend of mine said, you might want to try chemistry. I tried chemistry. 6 weeks later, I had a job, and I never looked back from that time. Okay. The importance of the G2 data set, we heard yesterday, the sort of history of this thing. So I always like to emphasize, especially to my physics friends, right? So I believe that the fact that it existed when you guys went ahead and did the tests of the density functionals was terribly important. The the fact that it was already established that sort of G2 theory agreed to the level that it did, about 1 kilocal per mole, with experiment, was crucial because people believed that those numbers were right. So when you then tested density functional theory against those numbers, there was no arguing about it, right? What the level of accuracy was. And we saw that over and over again when we were listening to the history. So having those benchmarks was terribly important, and that was, of course, one of Popel's contributions. Now, chemists and physicists, I believe in the room, we may have some chemists and we may have some physicists, right? So what people ask me, am I a chemist or a physicist? And my answer is always yes. So I thought about it, and I found a definition for how you can look into your heart and decide if you're a chemist or a physicist. And my definition is that a physicist would rather be right than useful. If you think about it for a while, right? I think I've managed to insult both sides. Later, to the one side of the physicists, even worse, are the mathematicians, right? And then on the other side of the chemists, as we'll see, there are the computer scientists. So how do I build these into this category scheme? Mathematicians are always right. Think about it. Okay. I'm Walter Cohn and non-covalent interactions. So one of the highlights of my scientific career was actually not being Walter Cohn's graduate student. That was a difficult time for both of us. But it was much later, when I was sort of more grown up, and I was working in density functional theory. But because I had gotten to know him when I was younger, and let's just say I wasn't shy about arguing with him, that I think we had about 10 years together after he won the Nobel Prize, where I was one of the few people who would still argue with him. And I think he actually appreciated that quite a lot. And also I knew his methods, right? He had taught me. Eventually I learned how to use them. And I knew most of his papers. And so I could sort of guess which way he would think on many subjects and sort of counter-argue against him. So we had many great conversations. And then one summer, I spent visiting him for a couple of months in Santa Barbara, and we worked on non-covalent interactions. And I discovered that if I would do a little bit of work, he'd have a paper that he'd written, and I'd understand the paper, and I'd say, yes, but there's sort of something missing here. And he says, oh, yes, that's in this previous paper. And I go back another 10 years. And we go back, and there's these Lesouche notes from the 60s, I think. And he was doing van der Waals back then. So he'd been working on it for about 50 years. And there were all sorts of interesting things. I have a collection of notes. We never published anything. And I was also aware that there were others who were working with him who had done other parts of this project. But I didn't know who they were. He hadn't told me. And we even proved some things. And at one point, it was clear to me he had a very deep insight into the origin of these non-covalent interactions. But none of this was ever written down. And so it died with him, which is interesting. One of the questions he always asked was, what is the small parameter in weak interactions? Why are they as weak as they are? And I don't think he'd satisfactorily answered that to himself. He also disliked rather intensely the expansion in powers of inverse powers of R. So that's just interesting, but it all disappeared. Okay. One little point I like to make. Some of you have heard We go on at some length about the semi-classical origins of density functional theory. Don't worry, I'm not going to talk about it this morning. But I just want to point out that I was in good company. So this was a project sort of started about 20 years ago. And at one point, I was explaining to a student sort of how a theory that uses this semi-classical limit would look. And the student, Attila Changi, Googled later that night to see if there were any papers in the literature that talked about this. And we were rather shocked to discover, okay, the resolution has gone bad. But this paper here, so I call this the really important paper that Cohn and Sham published in 1965. It's March of 1965, and it's about 6 months before the one that everybody was talking about yesterday. And they talk about quantum density oscillations, and you see at the bottom there, they're talking about semi-classical results. So now it's interesting, when we found this paper, I had sort of been aware, but not quite aware of its existence, because I had sort of not realized there was a second Cohn-Sham paper from 65. When you look up the citations, at the time, there was about 130 citations to this paper. Of that, 120 were mistakes, where the student had been told to look up the Cohn-Sham paper. But it's amazing to look at this paper. So this is what they were thinking of back in 1965, before they wrote down the Cohn-Sham equations. And back at that time, there were many people who were looking at doing electronic structure using semi-classical methods, like Bill Miller, for example, at Berkeley. Now I have to add to this part here a little story where Whiteout, you had organized a meeting at Duke in about 1999, was it?
6 or 7.
96 or 7. Okay, before Walter got his prize, I guess. Yes. But I had gotten my job, right? And so I had bought the bottle of whiskey. Okay, so I have to back up a little bit, right? It's a little unfair. It turns out I said something incorrect in my little talk last night, and would you believe we have fact checkers in the audience? So I could never find the email I had sent Walter, but David was able to find it last night. But I didn't send the one saying, "I'm proud of you." What did it say, David? It said, "Oh, congratulations, Walter. We chemists truly appreciate you." That's what I said. But then David found a second email discussing a bottle of Irish whiskey. And because I'd gotten the job, I wanted to give Walter a little token. It was a bottle of whiskey. I preferred Scotch. He preferred bourbon, so we had sort of settled on Irish as the... And so at that meeting, one night, a lot of people were talking about the constant in the Cohn-Sham potential. And Walter, being Walter, was like, "Kieron, what are they talking about? What's this constant?" So he wanted to have a party, but I had to leave the next day. So we just went about 10 p.m. to his hotel room. And we said we'd try the whiskey, right? So then I had to explain to him what the constant in the potential was. And he says, "Oh, yes, now I get it." And he says, "Well, you know, in the original paper, the number of electrons is held fixed. So if you want to do a density variation, you can push the density up at one point, but you must equally push it down at some other point in order to preserve the particle number. So then the other point, I can choose any other point as my reference. And so therefore, sort of no matter, as I move that around, I'll get this arbitrary constant that won't be determined because I can choose the reference point to be any value." So this was his way of thinking about why there was an undetermined constant in the potential. Anyway, by I think it was about 3 a.m. The bottle of whiskey was mostly gone, and I was begging Walter to allow me to go to bed, right? In the end, I think I just sort of had to leave, but he was still going strong, wanting. But in this conversation, he mentioned that he had done a calculation of a uranium atom embedded in an electron gas. So you take an electron gas and you put your uranium atom in it, and you could see these quantum density oscillations become the shell structure of the uranium atom. And so then, whatever, 15, 20 years later, I'm up at Santa Barbara, and I say, Walter, you know, I've looked for this paper, and I've not been able to find it, you know, but it's important. I need to understand these quantum oscillations. And he says, oh, Kieron, just Google it. You have all those modern tools. And I say, well, Walter, you know, I have Googled it, right? And I can't find it, you know. Do you remember anything about it, right? And he stops, and those of you who knew him might remember, he would just sort of stop and think, right? And once you learned not to disturb him, you wait, right? He thinks, and he thinks. And he says, I remember there was a conference organized by Kubo the next year, 1966. And I wrote something for the proceedings. I think it was that paper. And then he stops, thinks. And then there's a filing cabinet, and he goes over to the filing cabinet, and he looks, and he goes to the bottom drawer, and he opens the drawer. He looks at the things, and then he reaches in, and he picks out a preprint from 1966. There were still a few left in the drawer, and that was the paper. I immediately took it and scanned it, right? That's the book that it appeared in. But of course, he had actually cheated. This was his memory of his calculation of the uranium atom. I don't think that's a calculation. An interesting feature, though, is so he goes from having a very weak perturbation in the gas to having a very strong one, right? The calculation in this paper, he explains the concept of nearsightedness. Not in this one, in the original paper. They explain nearsightedness, and of course Walter forgot that he'd explained that in 1965, and it came back again quite a few years later. Okay, but that was just my warm-up. I haven't actually started my talk yet. Okay. Fossils and the future. So I don't want to spend time on the past. Okay, maybe the title of this slide shouldn't have been what it was, right? So we've seen a bunch of senior figures in the field yesterday and today. So maybe the left-hand side are the fossils. I mean, I shouldn't have said that. And these guys are the future, right? I had to make it up to Gus and Martin for giving them such a hard time at that meeting the other year. So yes, we're going to hear about the future today. So I'm going to talk a little bit about the future that's coming rather fast, which is machine learning. And the reason I wanted to bring it up is because we had some Nobel Prizes not so long ago in that area. So I'm not an expert in machine learning. I don't really like it, right? But I did meet an expert, Klaus Robert Mueller, at a meeting who taught me how to do it, and we did a lot of work together. And I've been doing machine learning applications in DFT ever since. And I'm teaching a course right now on the topic, and I've had, quite a few graduate students and undergraduates doing it. Okay, now this may seem a bit of a diversion. This is my clothes washer. So a few months ago, it died, and I had to replace it. And the new one is really fancy, and it has this dial on it where you could probably watch movies and things, right? This is the normal wash. This is towels. You could do towels, of course, right? You can do bedding, right? But then I found I could do AI wash. Right? It turns out I'm the only person in my household who isn't afraid to do AI wash. And of course, I throw in all sorts of things trying to trick it, right? So far, I've managed. Okay. One of the downsides of this machine learning or artificial intelligence in science is that many of the papers are not great, but that doesn't mean that there aren't some really good papers being done. It's just a little hard to find some of the good ones, right? And I first mentioned this when I was giving a talk to Paola's new place, Microsoft's AI for Science. And I was sort of felt a little awkward, right, saying that 50% of the papers shouldn't really have been published. And they all laughed, and they said, "You think it's only 50%? Okay. I have to mention, of course, a call out to young David. Young David, are you here? Yes.
I'm here.
Yes, way ahead. We heard about this yesterday, way ahead of the crowd, where they were using it to find the potential and also correctly put in the freedom of that constant, right? That was a topic of discussion around this time. This is, I think, maybe one of the more recent papers that I did. One of my students, Lee, went off to Google Accelerated Science, and a group of those guys, plus with a new graduate student at the time, Ryan Peterson, we did this cone sham regularizer. And I'm not going to talk much about my work, but what we did was we sort of actually set up the machinery to find, in a sense, the exact functional in this case, because we take the entire density. Now this was just done for these little H2 binding curves, but what we were able to do with this scheme that we set up is we learned from a very good graduate student in Japan so just look at the global one here. We trained on just 2 points. One is near equilibrium and one is stretched. So this represents sort of weakly correlated physics and this strongly correlated physics. And we had one validation point in between. And we were able to, looking at the entire density, create a functional which was chemically accurate for the entire binding energy curve. So having trained on just 2 points, you could then create a functional. And we could do this also for H4. If we trained on H4, we could get chemical accuracy. And then even we could take H2, interacting with H2 and get almost chemical accuracy, even though we hadn't trained on that. Now, one drawback I want to mention very strongly of I think almost all the work I've done using machine learning is that this doesn't generalize very well. It's designed, it gives you, say, good results for chains of hydrogen atoms. It doesn't necessarily work for any other element. And part of that is actually using the entire density, because if you think about it, our human designed functionals just look at the density, in a region and maybe a few other features, and you have to go back and pull out the sort of features of the density. You can't really use the entire density, but it is an illustration of the Holmberg-Cohn theorem in action. If you know the whole density, you can get the energy exactly. One reason that we sort of slowed down was DeepMind. This company in London produced this DeepMind 21 functional, which seemed to do everything very well. How many people tried out the DeepMind 21 functional here? Right. Yes, and my question is usually, so you tried it, has it converged yet? And the answer is usually no. So this was somewhat over-engineered, let's say, right? It gives you very accurate answers at the solution point, but not necessarily gets you there very fast, and it's very expensive. 2 years ago, I guess we got ChatGPT. Most people here. How many people have used ChatGPT? Raise your hand. There's no shame in it. Yeah. Very good. You could play these sort of games. You ask it to multiply two large numbers together. If you check, you discover that these are not. This is not the correct answer. A couple of digits are wrong, but that's because it's just giving you plausible answers. It's not necessarily designed. If you try this today, it will give you the right answer, because what it does is it writes itself a little Python code to multiply the two 4 digits together, produces the answer, and then tells you what it is. And that way it gets it right. And then about a year ago, my friend Dosh, who was on that paper, produced all this work with all these new materials relative to the materials genome project that he'd gotten using Google's leftover CPU cycles. So this greatly expanded the materials genome stuff. How's my time? Okay. So I just want to do a little distraction to something completely different. We're talking about DFT in chemistry, but there's more than one kind of DFT. There's something called classical DFT. So the classical limit of the Holmberg-Kohn theorem. And it's for classical fluids at equilibrium. And just like with our electrons, in principle, you can find a single equation determining the density of the liquid, of the fluid. It's the h bar goes to 0 limit of Mermin theorem from a friend of mine, Bob Evans, proven in 1979, so that's some time ago. And so for a classical fluid, if you have this functional, you don't need to do molecular dynamics even, right? You solve directly for the equilibrium density of the fluid. So the particles are not the electrons, they are the units of the fluid, like the water molecules or say argon atoms, if you're looking at argon. But the problem is that every fluid has a different functional, because every fluid has a different interparticle reaction, and it can even be 2, 3, or 4 body interactions, right? So in 50 years, there's been almost no progress in making density functionals. And that looks like it's just about to change. So a friend of mine, Matthias Schmidt in Germany, and a very good young graduate student, I've been advocating for about 10 years to try machine learning seriously on this problem. They did. And then also just 2 months ago, there's a new preprint now with Bob as one of the co-authors, and they have some really outstanding results. And one of the things is that they can train, they just do Leonard-Jones fluids, but they train in one phase, like in the liquid phase, and they get excellent results in the gas phase. And they can also show, and vice versa, and they also find that the exponents of the phase transitions are different from mean field exponents, which they don't even quite understand how it can manage to do that. So that's on the archive. And so, okay, so paradigm shifts, right? This term was introduced to discuss what happened with quantum mechanics at the start of the 20th century. Planck identifies H in 1900, but the Schrödinger equation is 1926. So paradigm shifts do not occur overnight. You could have an entire scientific career studying quantum mechanics without ever seeing the Schrödinger equation, as to a certain extent Pauli did. But of course, paradigm shifts are accelerated when there's a Nobel Prize in physics and a Nobel Prize in chemistry based on machine learning. Jeff Hinton used to work for Google. Apparently, even he's confused as to why he won the Nobel Prize in physics. Dennis Hassabis, this is the AlphaFold, which has had a huge impact on the protein folding problem. And those two are from DeepMind. Half of the prize was for DeepMind. Okay, and if you want to understand these things, the NSF budget is $9 billion, NIH is $47 billion, but OpenAI, who invented ChatGPT, $86 billion. Now, I made this slide in February. Sadly, if I checked last month, and this is now 157 billion. Should have bought some stock, right? Students, most of them now go off to these high-tech companies. You can't, no matter how good they are, they have so many other possible demands on their time. The old masters of the universe, so they merged Google Brain 18 months ago. My friend Josh now works with them. I talked to them January of this year, and I started consulting for them summer of this year, and I can't tell you anything about it because of a non-disclosure agreement. They are not the same as academic people at all. Okay. So yeah, this is the sort of main picture I wanted to leave you with. So we have high-level quantum mechanics, couple cluster, QMC, DMRG. We have density functional theory. This is sort of orders of atoms that you might think of calculating. Molecular dynamics with classical force fields, and in principle, classical DFT. So one can imagine bridging these length scales. And the one that's coming fastest is this machine learning potentials, first done, I guess, by Baylor and Paranello in 2007. Then one can also imagine training a density functional from high-level quantum calculations to getting a machine-learned exchange correlation functional. Lots of people are trying to do that. And now we can imagine, thank you, getting classical functionals to do equilibrium fluids by training on the MD. So at every point along this way, we have this machine learning helping us bridge these length scales. And all these things are well-defined objects, right? It's the finding of them that's hard. But once you find a functional, then off you go and use it, right? Regardless of where that functional came from, regardless of how many empirical parameters there might be in it. Now, one thing that's happened in the last year is the machine learned potentials have moved sort of to a new phase. They talk about foundational models where they've trained them for all the elements in the periodic table. So there's this really important paper, MACE MP0, mostly from the Cambridge crowd. And this picture is just showing all the different systems that this potential can do. It isn't it's trained on DFT, but it isn't as accurate as DFT. But basically, it gives you reasonable results for all these different problems, and then you can retrain it to give you DFT accuracy. This is from a friend of mine, this carbon shock simulation. It's an MD with 18 billion carbon atoms. This is from Aidan Thompson using the LAMPS code. Using a machine-learned potential, but in principle, it should be giving the same exact results as DFT. And the idea is that it's a shock passing through a chunk of carbon. These are different lattice structures that you see. And imagine if we could now do this with this classical DFT. You could do this in seconds, right? You could do this sort of calculation. Cruel things folks say about my work. None of you guys would say this. In fact, he who is without sin may cast the first stone. Some of you may recognize this unsystematic, right? These density functionals, making them up. They're unreliable. We don't have any error bounds, right? Full of jargon, self-interaction, delocalization. Not real science, right? Because you're just making some. Can only be learned from a guru, right? Too many choices, right? But am I talking about DFT 27 years ago or machine learning 2 months ago, right? It's quite eerily similar, this list of problems that people have. Rethinking the Kohn-Sham equations. They literally turn an NP-hard problem into a P-hard problem, right? Of course, all the difficulty is embedded in exchange correlation, but with the simplest formulas, right, it ends up in n cubed scaling, right? So what does it do? It gives you a approximate solutions to this very difficult quantum problem, but not ones that you can refine and make more accurate. So in a sense, it proves that the density is the ultimate feature. Once you have it, you have everything. And I'd say my machine learning work illustrates this. Is there a machine learning equivalent of the Holmberg-Cohn theorem? I'm almost sure that there is, but I can't quite figure out the math to write it down. So I'm going to summarize. Well, these are the things I've said. Thank you very much for your attention.
So, time for some questions. Gustavo?
Thank you very much for fantastic talk. Question about machine learning exchange correlation. Is it possible to place the machine learning exchange correlation functional to relate it to the steps of the Jacob's ladder? Where are they?
Well, so there's sort of two flavors, I would say. One is where you take a human design scheme, like an approximate form that John has thought of, and you try to get a better version of that than the one that John has made up, right? So that's one game. So those are trying to make human design ones better. Then the games I've been playing have all been where the functional looks nothing like the original. So there are these different types, right? So my ones are totally non-local. They tend to prove points of principle, but then they don't tend to be useful in practice yet. Yes. And so both kinds exist in the literature at present. So far, I don't think anyone has come up with something that's significantly better that people will be inclined to use. The advantage of using the human designed one is that the ingredients you can put into libxc. You can put it into a standard library and everybody can immediately use it. The DeepMind 21 functional was a slightly obscure, range-separated local hybrid, and so some of the ingredients were a little unusual and expensive to calculate. They don't have to be that way.
David?
You mentioned the impact of machine learning on electronic structure, but you don't put on that list the use of machine learning in more conventional wave function theory.
Right, because this is a conference about DFT. And yes, it is having a significant impact in sort of, well, I know mostly about QMC improvements, like Frank Noah's thing, and some work that Paolo has been involved in lately. And there they actually do accelerate, I mean, make QMC a good deal faster, but they still have a way to go to try to compete with DFT on systems of large size, right, in terms of computational cost. But that, yes, there's a whole bunch of work on that too.
Other questions?
If I may ask another question, so we are talking that kind of mass potentials often say trained on DFT data, but we all know that DFT is very, very different. I know that materials project has more or less controlled way of what is their DFT, but we also know that DFT data is sometimes extremely wrong.
Yes.
Like strongly
yes,
correlated
absolutely.
systems which are in the data. So what are we doing with all these potentials trained on the data which...
So the value of one of these foundational MLP models is not that it reproduces DFT accuracy. It's that it gives you a sensible description of the system. Then you can sort of sample and look at what is going on in lots of configurations and so on, and try to figure out where the science is. You can then do delta learning to refine the model to hit the DFT accuracy. And in this picture that I've made, right, the idea is that in the next 5 years, I believe this is going to transform a lot of material science and chemistry that's related to that. The fact that everybody can run these potentials. But at the same time, hopefully somewhere somebody comes up with machine learned density functionals that are trained on quantum chemical data that are higher accuracy than our current ones. And so then you feed them in to the machine learned potentials, and you get a foundational model, etc. Right? And then I'm hoping also people will really start working on that last piece. And then you could imagine doing, so then you get all the way from quantum mechanics to macroscopic matter, which is something I think people have talked about for a long, long time. And I think machine learning is the way to go to make those connections. That's what it's really good at.
Sure.
Bridging time scales.
We'll draw questions to a close here. We thank you very, very much, Kieron.
Thank you.